queues are another fundamental data structure in computer science and programming. And in today's video, I'll go over how queues work and another specific type of queue known as a circular queue. Now, a queue in computer science can be thought of very similarly to a queue in real life. So imagine you went to a coffee shop, and when you enter the coffee shop, you see a queue of people behind the counter waiting to get their order. Now, you won't enter that queue from the front or the middle because people waiting before you, and it's quite rude to do so. So you enter the queue from the back. Now, the person at the front of the queue, who's getting the order, they will leave first because once they get the order, they just leave. So if you think about it, the person who enters the queue first is also the first to leave. So it follows the operation of first in, first out. And in queues in computer science behave very similarly to this way. Behave very similarly in this way to real life queues. So I'll get into what I mean by that with an example. So imagine here I have an arbitrary element 1, or you can think of it as a person in a queue if you're thinking about the coffee shop analogy. So let's add some more people to this queue, right? So we've got 3 people right here. Now, an important thing to note is the front and back of a queue is going to be inverted when we're programming it. So 3 represents the back of the queue and 1 is the front. And that's an important distinction to make because when I was trying to learn queues, I got confused about this as well. Because you think about, well, you add from the, you remove from the front and you add to the back, but it's behaving the opposite way. You have to remember that the front of the queue is the back and the back of the queue is the front. Well, in computer science, the data structure, that's how the queue works. So if I want to add elements to the queue, that's called an enqueue operation, right? So here I enqueued 4 onto the queue. So I enqueued 4 onto the back of the queue, remember? Because 3 was previously the back, now 4 is the back. So if I add another element, 5, enqueue it, and then add 6, this is how the enqueue operation looks like. And now the obvious question after that is, how do I remove elements from the queue? And which side do I remove elements from? So with the dequeue operation, you remove elements from the front of the queue. And the front of the queue is represented by the number 1 in this case. So I dequeue 1, now I dequeue 2, and this is how the dequeue operation works. So the enqueue and dequeue operations, they're just functions we call in our code. The way we know what the front and back of the queue are is through these 2 pointers known as the rear pointer and the front pointer. And as the name suggests, the rear pointer points to the back of the queue and the front pointer points to the front of the queue. So now we'll go into programming a simple queue to see how these operations work in practice. So here I have a basic hello world example. So we're going to first create a struct to hold the queue. And the struct's going to be quite similar to the stack we had in our previous video. So I'm just going to create a struct and name it queue. And we need, well, in our stack before we just had a front point, we just had a pointer pointing to the front of the stack, then we had the stack itself and the size. It's going to be quite similar with the queue but a bit different. So we're going to first have our data, right? So let's just say 10 elements. I'm going to store this value in a macro right here called define, let's say queue max size, I'll call that 10, and then that's just going to tell us the max size of our queue. We're going to have a size variable which is going to be, well, queue max size, and we're going to have a front pointer and a rear pointer. Now you may be thinking, if it's front pointer and back pointer, shouldn't these actually be int star, which basically means this holds a memory address pointing to an integer? And that we can do that, but we can also just store indices instead of pointers, and I think that's a lot easier to understand and a lot simpler when you get introduced to queues. But you can also use pointers if you want. It's just it's up to choice. Pointers might be a bit more efficient because we're not because we aren't using integers directly, we're just referencing memory addresses, but it doesn't really make much of a difference. So let's create our queue. Let's call it queue, and we're just going to initialize everything to 0 at the start, right? Now let's start off with the first operation, which is enqueue, and that's adding elements to the back of the queue. So let's have a boolean which so we're going to tell us if we can enqueue the element properly or not. So if we do enqueue, we need to pass in a queue, and then we also need to pass in the data we want to, or the element we want to add to the queue. Now we're first going to check if data at size is less than queue max size. And initially the data size variable is set to 0 because there's nothing in the stack. And as we add elements, we're going to increment this. So this will tell us if the queue is full or not. If it is less than the max size, that means we have space in the stack. Sorry, not the stack, the queue to hold data. So we say queue at rear pointer, or rather queue at data, queue at rear pointer is going to be equal to the element. And then queue at rear pointer is going to increment that. And we'll just return true. So as you can see, we just add the element at the rear pointer, then we just increment the rear pointer. And if the queue is full, then we're just going to return false. The other operation we have is dequeue, and that's removing data from the queue. So we're going to return the variable we actually remove, and we have to pass in the queue. So we first have to check if the queue size is greater than 0, because if it's not greater than 0, then the queue is empty. We can't dequeue anything. So if the queue size is greater than 0, we just look at the element at the front pointer, which is pointing to the front of the queue where we dequeue from. We just call this thing element. Then I will just set the value at the front pointer right now to 0. You don't have to do this, but I just find it easier sometimes when you're trying to debug things, because the old value can persist in the front pointer. Sorry, the old value can sometimes persist in there. This won't make sense what I'm explaining right now, but once you start to see how the program runs, the old value can sometimes persist, and then we can have some issues when we're trying to peek at the data. So once we're going to set that to 0, and then we just return the element, right? Actually, no, before we return the element, we need to increment the front pointer. And if we don't have space in the queue, we just return -1. Sorry, if you don't have any elements to dequeue, so the queue is empty, we just return -1. And there's one final method I want to fill out, which is called peek. And peek just tells us the value at the front of the queue. So if the queue size is greater than 0, we just return queue at data and then queue at front pointer. And then if it's not greater than 0, we just return -1. And we can just treat -1, or the user can treat that as an error message. Now we don't actually have to pass a pointer, just realized, so we can just make a copy of the arrays. So make a copy of the queue struct, because we're not modifying anything here. So let's test this out, right? So we're going to first enqueue, let's say queue 10, and then we'll just peek at the queue, right? Let's do peek queue. Is compile? No, it's not compile. Undeclared identifier. Okay. It should be queue. Okay, compiled. Let's run it. So first we got -1 for peek. Why is that? Okay, that we forgot to increment the size. Let's do that. So that's the wrong one. It's supposed to increment the size here. And also, I forgot to do something else. Just reminded me you have to decrement the size right here. So that's a good bug. So we got 10, right? So let's say we enqueue some more data onto the stack. I mean the queue. Let's say 20, then we do 30. And when we peek, we get 10 3 times. Now why is that? Well, if you remember, I said that peaks at the front of the queue, and the front of the queue is always going to be 10. So if you want to see the other data in the queue, we have to dequeue them first. So I'll show you how we can do that. If we dequeue right here a few times, then just peak. So let's do that. Let's run it again. Okay. So you got 10 a few times, then we dequeued, and now the front pointer points at 20. We dequeued again, and then the front pointer pointed at 30. And then we dequeued one last time, then the queue was empty. So we just got -1 because nothing else in the queue. Now, if you were paying attention before, you might have noticed a bit of an issue there. And the issue with the traditional queue is we end up having a bunch of empty space in the queue, but we can't add any data to it. Now, that doesn't make much sense, we just saying it like that, so I'll show you by an example. Let's say we have this example queue, which has a maximum storage of 7 elements. If I was to dequeue here, we dequeue from the front, we get to 4 now. Dequeue again, we get to 5. We dequeue again, we get one last element here. Now, let's say we enqueue7 onto the queue, then we dequeue6. We're left with one element. Now, the rear pointer cannot be incremented because then it will reach the max size, right? But we also have 6 empty spaces right here. So what's going on? Well, this is a fundamental problem with the logic of a traditional queue, is that when we enqueue and dequeue, over time we start to reach the end of the queue. And then because of the logic that we're just checking if the rear pointer is less than the queue's maximum size, we don't know that there's actually space in the queue. So you may be asking, what is the solution to this problem? And that's where something called a circular queue comes in. So a traditional queue would look like this. If we rearrange it a bit into this form, we have a circular queue. And I'll explain what that means in a minute. So let's say we have our rear pointer and front pointer at these indexes, and we'll just remove some elements here to show the example of how the circular queue works. Now let's begin dequeuing elements again like before. We dequeue6, we dequeue7, we dequeue1, and we've reached the rear pointer. What you might have noticed before, if I just go back, is that the front pointer and the rear pointer can wrap around the array. Sorry, not the array, wrap around the queue. So 7 would be the last index if we're thinking about this as an array. The front pointer can wrap around the array, which is a very powerful feature of the circular queue. So I'll explain why that's important. So we wrap around and we get to 2. Now in a normal queue, this will be a situation where we can't add any more data because the queue is full, but it's not really full because of remember the size comparison problem. However, with a circular queue, since the pointers can wrap around, we always know if there's space, so we can enqueue and just increment the rear pointer, and it can wrap around the whole queue as long as there's space, right? So I am back here on the code, and I'm going to make a few changes first. So I realized from the previous example, we should also have an occupied variable, because right now we're just comparing against this macro called qmax_size. But if you want to have queues of different sizes, then this isn't really practical, because you have to create a new macro for each one. Sorry, this macro would mean that all our queues are 10 elements long. So in order to prevent that, we're going to have an occupied and a size. So size will be the maximum number of elements in the queue, and occupied will tell us how many elements we are currently using. So if we have 7 elements and we can have in total, and I'm storing 3 elements, then I know that there's still space in the queue to add more elements, right? So we're going to first change this line. So I'm going to say size in this case is equal to qmax_size. Now this syntax is the struct initialization syntax. What it basically means is that size will be set to qmax, and all the other variables or the struct members will be set to 0. This is a very powerful part of C and has recently been added in, I think, C++ 14. was in C. It was introduced in C99, so C++ adopted it quite late, but it's very useful. So we have size equal to q max size and occupied front pointer rear pointer equal to 0, and data has been initialized to 0. So here we're going to make a few changes. So we're going to first check if the occupied number, so the number of elements which are occupied is less than the maximum size of the queue. And if it is, we're just going to change the size to occupied, because when we add elements to the queue, or a circular queue in this case, we're going to increment the number of occupied. We're going to increment the occupied variable. Now, the part when I was talking about wrapping around the queue, what did I mean by that? Well, here we're just incrementing the queue by this, so it's adding plus plus. The problem is we eventually get to the point where, let's say size is 7 and our index is 6, so we reach the end of the array. We can't, if we try to index more than that, we've reached index out of bounds. But elements 1, 2, and 3 might be empty because we just dequeued from the front. What that means is we need to be able to wrap around the queue, so reset the index back to 0, and then check the slots. So not check the slots, but just check the array there, because there should be space. And we know there's space because occupied is less than queue size. So how do we do that? Well, we use the modulus operator. So we say queue rear pointer plus 1. So we're just checking if the plus 1 means, let's say we're on 6. So it's 7, we're going to do, so let's say queue size. So this makes more sense. So we're checking, let's say we're on element 6 and size is 7. Is the next element going to be the end of the queue? So are we at the end of the queue right now? So 6 is the end of the queue. We add 1, we get 7. 7 modulus 7, which is queue size, is going to give us 0. So we come back to the start of the queue. And this logic is what allows us to wrap around. Now, because of the order of precedence in C, I have to add brackets around this part. So we get this, and then we just increment occupied. And a similar thing happens here. So we just check if the number of occupied elements is greater than 0. This decrement occupied. And we do the same thing of wrapping around the queue with the front pointer as well. So we do queue at front pointer plus 1 do modulus queue size. And then compiled, and there we go. So there we go. It looks the same right now, but we don't have that issue of running out of. We don't have the issue of reaching the max index of the array holding the data for the queue, and then having a bunch of empty space at the start because we dequeued from the front. So I hope this tutorial was quite useful. If you did enjoy it, please like, comment, and subscribe. If you have any recommendations for other tutorials you want, you can just comment that down below. I'll look at it. And also, the next video is going to be about pathfinding algorithms. So I'll show you how we can practically use the queue and a circular queue. And yeah, thank you for watching. If you want to check out the previous video about stacks, if you found this interesting, that should also be interesting.